All right, let's talk rotational motion, and let's use what I call analogs. We're going to use a wheel so that we can talk about things rotationally, and we're also going to use things that you already know, linear quantities, and show you their analogs. It's not exactly the same, but it's pretty close. Also, there may be some noise outside. They're doing freshman orientation. All right, the first thing that we do with when we're in physics, generally we start with something simple. We start with distance. Distance is in meters. Well, what about rotationally? If normally I'm talking about a distance from here to here, because physics in science we're always trying to measure things. Well, I'm measuring this distance is different than this distance. Well, rotationally, how does that work? You'll notice this yellow mark right here. That might be a little easier to see here. Well, this distance, rotationally, would be different than this distance, and we need to distinguish that. Well, what do? We could use angles, we could use degrees, etc., but we use radians. And we call that angular displacement. And I'm going to put in radians. Now, what is a radian? For me, the easiest way to remember that, if you have a unit circle with 1 meter, an entire circle is 2 pi radians. So we have 2 pi radians equals 360 degrees. Why I put it in parentheses, I don't know. Okay, after that, well, it would make a difference if I'm doing one circle, or sorry, if I'm talking about a particular distance. Well, if I do that distance faster, we know we have a different velocity or speed. Well, this obviously takes a very long time to do one circle, or that. Well, obviously, it's the difference of how fast that happens. So I guess we need to talk a little bit real quickly about time. Actually, I'm not even going to write that down. Time is the same. It's in seconds and seconds. There's no other way of using time. But the idea of angular speed. Well, here we could say speed or velocity. And of course, you should know that speed is a scalar, velocity is a vector, which means it has direction. And by the way, if you think about there being an arrow like this, that's your velocity. Whichever way you're moving, that's your velocity in a straight line. That would be in meters per second. And we, I guess we could also write down that speed equals distance divided by time. Well, over here, we have angular speed, or angular velocity. Well, that would be in radians per second. And that equation would be your angular speed, which is omega, would be theta divided by t. This would be, this would be theta. Which again, you've used for angles already. Notice here, speed equals distance divided by time. Omega equals theta over time. Okay? Well, now that we have that, obviously, what if you sped up, but you sped up in, direction for angular speed. If I take this and I wrap it around, my thumb points upwards. That would be following the direction. That would be a positive angular velocity, negative angular velocity. Now again, don't do this. This means nothing. Your thumb, as if it's on a shaft or on a rod, positive angular speed, negative angular speed, or positive velocity, negative velocity. Well, the next thing that we do, what about acceleration? We speed up, which is, of course, as you're already noticing, we're just dividing by time again. Acceleration, which would be change of velocity over time, is in meters per second squared. Well, this would be angular acceleration in radians per second squared. And that equation, alpha, otherwise known as Jesus fish, alpha equals change of angular speed over time. Okay? Now, once we've gotten that, then generally I would go to force next. Well, here, if we have force, and you know that that's going to be in newtons, and F equals ma. Those are the things we know there. Well, what about a force? A force causes an acceleration in a straight line. Well, what causes an acceleration here? You might say, well, look, that's a force. Well, but that force and this force are not the same. If I push if I push to the center, I get a particular force. I push here, I get more acceleration. And of course, you should be thinking right now, that's something that we call torque. And torque, we use tau. I guess if I want to call it, that's alpha and omega. You should already know omega. You should already know that that's theta. Okay, well tau, if force equals mass times acceleration, what in the world is this mass thing? Well, we'll come back to that in a second. First of all, our definition, and 3 lines means is defined as a force, and as we notice, times a distance. So the longer away you are, the greater torque you have. And so I'm going to do this, a force perpendicular to a distance. The actual way that we are going to do this is going to look like this. R cross F. And those arrows show that they're vectors. This symbol right here, known as a cross product. A cross product means that you want perpendicular components only. Why the distance, R, is ahead of the F, we'll explain later on. Well, usually, as you'll see, as you've seen in these others, the idea that one can go directly to the other, we're going to do that next. Torque does cause an acceleration. We notice that as we're doing this, if I push, I get an acceleration and the thing will speed up. So that's just like force causing acceleration. So we need to have this idea of mass. If you will stand up, take your hands, and you'll do this at some point, and you do this. And I'm going to ask everybody to do this even though you're just watching. Okay, stand up so you're not going to bump into your neighbor. And if you do this, you'll notice it's easy to turn your body. But as you take your hands and you move them to here, you'll notice it's harder to move and more resistance to stop. Isn't that what mass is? Mass is a resistance of change of velocity. You have a heavy object, it's hard to get it going and harder to stop it. A lighter object, easier to start moving, easier to stop. Well, that's easy to twist or rotate. This is hard to rotate and hard to stop rotating. Therefore, there's something that depends on mass, but also depends on its distance from the axis, distance from the pivot. And that's known as moment of inertia. I'm going to put that over here. Actually, let me use another color so it doesn't get lost. I, moment, and there's the freshman outside, inertia, meaning that it has inertia around a pivot, and that equals roughly mr squared. That mr squared is for a point mass, your hand being a point mass. Rods and different things, as you probably remember from the previous year, that's a bit different. So there's generally some sort of term here, a 1/2, 1/3, something like that, that changes that depending on the configuration. Well, this also gives us, it's not just in kilograms, because it depends on distance as well. And notice it depends on the square of the distance, so the distance matters a lot. Well, that's kilogram meters squared. So I is in kilogram meters squared. That's moment of inertia. So, using I, moment of inertia, for F equals ma, and we get F, which is torque, equals my mass, moment of inertia, times my angular acceleration. There you go. Those two would be their analogs. Those would be the equivalents. F equals ma, torque equals I alpha. More torque, more angular acceleration. More moment of inertia, less angular acceleration for the same torque. And I guess we probably should write it this way. We'll do that. Torque, or alpha, equals torque over I. So the angular acceleration is directly proportional to the torque you apply, the force times the distance, and it is inversely proportional to the moment of inertia. The more mass you have at a greater distance, the harder it will be to accelerate it. I apologize, I didn't give the units for torque, but you will notice that those are newtons times meters. Okay? And I'm going to write it that way, Newton times meters. There is no special unit for that. It is Newton meters. Okay? I'm going to do one more, and then we're going to have to erase this and start over. So, next, force, etc. Oh, well now let's do work. Well, work equals force times distance. Well, force is torque. So work equals force and distance is theta. Now that looks a little bit different. Now notice I called it work. I didn't call it anything else. So if I have this here and I push and I give it a torque through a distance, this would be through a distance. I can't really think of a different way of doing it. I can't pull this way, that's not a torque. But notice, if I push this, the greater the distance I push it, the greater angular displacement I push it, the greater work will be done. Okay? Now, of course, if I do greater work, now you might say, what are the units there? And the units here would be Newton meters times radians. Newton meters for torque times radians. Turns out that radians are a nothing unit. They disappear like degrees. Why? I'm not exactly sure. It just does. Notice this one is Newton meters too. And this one's Newton meters. But this one's torque. And this one is work. And work has the units of joules. And this one has the units of joules. So how is it that this Newton meters equals joules and this Newton meter doesn't? Well, the difference is this one is, just as when you do work on an object, let's draw this. So if you have an object, M, and I'm trying to push it this direction, and it moves a distance. Well, and let's draw it here. Well, this force, this component of the force does work. This component of the force does no work. Well, if torque, so work is actually force parallel to distance. This is perpendicular. This does no work. It provides torque, but it does no work. This one, okay, so imagine that I have this locked in and it can't move. Or even, yeah, I mean, I had like this right here. I push on this. I'm torquing on it, but it's not moving, so I'm not giving it any kinetic energy, therefore I am doing no work. But if it moves, now I get work. Okay? So let's go ahead and erase a little bit of this and we'll go and do a little bit more. We're pretty close here now. So we just talked about how work can create, so let's remember our basic definitions of work and energy. So work is force times distance, but work is always a change of energy. If work is done and no energy is created, then, if you think work is done, but it does not change energy, no net work was done. You can do, I guess, work, but not have any net work done. So, let me erase this a little bit better. Okay, so we said that work equals force times distance, and I'm going to put equals a change of energy. Well, what is that change of energy? It could be potential energy, it could be kinetic energy. What about potential energy? mgh. Well, m we know, but that's potential energy. Let me just break it to you. There is no such thing as rotational potential energy. So there's none. Okay, and here we said that work equals torque times theta. Well, that change of energy, what about kinetic energy? Kinetic energy equals 1/2 mv squared. You have an object that's moving. Does it have energy? Yes, it could bump into something and create a force. Well, that's energy. Likewise, an object drop can bump into something and cause a force. Well, what about a rotational object? Can a rotational object hit something? Well, let's imagine this had a lever on it. It could hit something. Notice that if I touch it with my hand goes down. So it can create forces. It can do work. Well, let's see if we can move it over. Kinetic energy rotational equals 1/2 m, which we said was the moment of inertia, times omega squared. And since it's still kinetic energy, that'll still be in joules. Okay, simple enough. Power. Power, our basic definition, is work over time or a change of energy over time in watts. Power. Well, this would be force times distance over time, which is force times velocity. Okay, actually Tipler uses that one more than this one, but I like this one. And what is theta over time? Wow. Notice once again, power is force times velocity, and the analog of that is force, torque, times velocity, omega. It still works. Next one, if we go into, okay, momentum. Momentum, little p, equals mv. Well, here we use L for angular momentum. By the way, this is still in watts, because that's meters divided by time, which is still a watt. Angular momentum, what is m again? Well, that's I. And what's v? Omega. This is not the same unit, not the same letter, not the same unit. But it does have something that's very similar. If something has, okay, mass is defined as its ability, mass is a measurement of inertia, how hard it is to get something moving or to change its motion. Momentum, however, is different. Momentum is how hard it is to stop something from moving. A large object may have a lot of inertia, a lot of mass, but it has no momentum if it's not moving. Hopefully your house has no momentum. But what about this? Can you say, oh, that has some sort of momentum? Well, if it has some sort of momentum, linearly it means it wants to keep going in a straight line. Does this want to keep going in a straight line? It's hard to tell. It actually does. Let me show you. This wants to keep going in a straight line. It's starting to fall over due to gravity. And actually I can take this, and if I had a rope or something, I could do, I can kind of do this. There you go. And that goes around like this. And what you should do at this point, and I have a couple of these around the room, you should take it, and you should point towards the ceiling. Okay, I'm going to point this towards the floor. It went that way. It is fighting me. It wants to keep going this direction. Remember our direction? That's angular velocity, and that's the direction of its angular momentum as well. Okay? And remember that scalar scales a vector. This is a vector, it has direction. This is a scalar, it has no direction. Therefore, whatever the direction of the angular velocity is the direction of the angular momentum. The last one I'm going to do, there's not an actual symbol for this, but you should remember that momentum equals, a change of momentum equals impulse. Now, some people use, I've seen I's, I've seen J's, all sorts of things, and impulse, J, equals force times time. Well, there is no angular impulse symbol that I've ever seen. So I'm going to say a change of angular momentum equals force times time. And if you work out those units, you will get it. Well, just what are the units for angular momentum? That would be kilogram meters squared times radians per second. And remember, radians is a nothing unit. Kilogram meters squared per second. Those are the units for angular momentum. Now, with this knowledge, you should be doing some, I've got a worksheet, this is in case I put this online, where it goes through linear and then rotational problems. You need to, if you get stuck on one of your linear things, go back to your if you get stuck on rotational, think linearly. What would that look like if it was rotating?